Thank you all for joining us today. We'll go ahead and kind of get started. We've got a few announcements to make. Welcome everybody. Just a few things. We have any of y'all that made our luncheon, our last luncheon, the scholarship awards have been announced, the 5 scholarships that were selected, and they've been properly notified. They'll be posted on our website. Jeff Sibley, our education chair, has previously announced their names. I don't have the list here, but those will be posted on our website. And that was a great accomplishment, I think, for the section to get this program up and going again, so we plan to continue this in the future. I wanted to mention a few things. We've got some new members that have joined us. We appreciate that's kind of our lifeblood of the section, of course. The new members, and I don't know for sure if these are some that had left and rejoined or not, but I'm going to go ahead and mention. We have John Butler with Emerson. We have Clinton Cottle with the Eads Company. We have Sharon Drake, Dow Chemical. Donald Upton of Plant Services. Alan Hungerford, Chesley Hungerford of Oxia. And Dr. Lee Tao, Dow Chemical. Are any of y'all here today? Okay, we got one. Well, anyway, we're glad to have y'all and appreciate it. We find out we have members benefiting from a lot of things. Sometimes they may not attend the lunches, but fortunately there's a lot of other benefits of ISA membership that they partake of. So the other thing we want to mention, we have our scholarship golf tournament is going to be coming up on April the 12th. Perry Higgins is here. He's handling that for us. Perry, you got room for more teams?
Sure do.
Good. All right. We've got that coming up. April 25th is our tabletop, which is one of our primary fundraisers of the year. So I know that Paul Rogers, our chairman for the tabletop, has sent those notices out. If anybody hasn't seen that and they're interested, please let us know. There's information here regarding that. Ending our season, we kind of run through, we kick off in September and run through April, so our last luncheon of this season will be next month. And following that, we'll have a membership drive and fish fry, which is coming up May 9th. And this is going to be the theme of this year's we haven't done one in a while, but our membership drive theme is going to be about accelerating your career via ISA membership. So it's going to be, I think, very entertaining. There'll be, I think, some nice testimonies about ISA membership and what it's done for some of us. Me in particular, I have benefited greatly. We'll talk about that and some other things. We'll also have some additional entertainment. I think for those of you that thought Elvis was no longer with us, I'm here to tell you he's alive and well and doesn't at all look his age. He's going to be there to entertain us. So, among other things. Separate from Brazos Section, we have a couple of other sections. I want to mention their tabletops that are coming up. Texas City is March 21st, and Texas Channel is April 4th. And those will be posted on our website as well, isabrazos.org. So, again, thank y'all for coming. And we're going to get Mr. James Young, our program chair, up here to introduce our speaker today. Thank you.
Thank you, Phil. And I want to also say welcome. This is our 7th program this year, and we will have one more program in April. We usually put on 7 or 8 programs each year. We try to focus on technology topics so that you will find value in that in your job as an instrumentation and automation professional. Please sign in on the sign-in sheets before you leave. We need those head counts so that we can determine how much lunch to bring in. If we don't bring in enough, then some people go hungry. We hate that. Our speaker today is Jacques Smuts with OptiControls. The topic is troubleshooting and solving poor control loop performance. This presentation will explore various reasons why some control loops can be very challenging and explain how to get the best performance from these loops. To help with troubleshooting control problems, he will show a fault tree that helps divide control problems into different categories so you can target the trouble. Presentation provides steps to follow for isolating problems and troubleshooting poor control, and also some corrective actions that you can take to to improve your response. Jacques Smuts is the founder and principal consultant at OptiControls Incorporated. He has more than 20 years of experience in process control and loop optimization. He's trained hundreds of engineers and technicians in process control and loop optimization. He's a licensed Texas professional engineer and a senior member of ISA. He's also author of the book, Process Control for Practitioners. He received his PhD in mechanical engineering in 1997 from Johannesburg, South Africa. Please welcome Jacques Smuts.
Thank you, James. Can everyone hear me? Well, I know it's customary to start off with a joke, but I've tried that. My jokes really aren't funny, so I'm just going to skip over and get right into the technical stuff. That's not exactly what I mean. All right. So I'm going to talk to you a bit about troubleshooting control problems. And, well, who of you has a control loop back at your plant? Yeah, kind of a silly question, but yeah, we all have control loops. And bigger plants, who of you have no control problems at your plant? Like, all of your loops run just really, really well. Makes sense. So that's exactly what I'm going to target here. I'm going to talk about problem control loops. I've been doing this for a long time, and if we apply the 80-20 rule, we can come up with just a few problems that occur very commonly amongst different control loops. The loop doesn't perform well. Why doesn't it perform well? Well, because it's oscillating to less friction or whatever the case might be. So I'm going to go through a kind of a fault tree here to talk about the different control problems and how to solve it. I'll start off, this is not really in sequence, it's more topics that I'll cover as I go through the presentation. But I will talk about symptoms of poor control, various symptoms. I'll be talking about oscillations, a very common problem. Sluggish response from control loops, the loop just doesn't get back to set point as quickly as you want. Large disturbances, noisy control loops. Then I'll differentiate between internal and external problems. Some problems originate within a control loop, so we know where to find it. But some problems originate external from the control loop. It affects it from outside. So how to differentiate between these two problems? I'll be taking a look at poor controller tuning, control valve problems, and then I'll use as a tool for the entire presentation, I'll use a fault tree like this. So I'll basically cover all these nodes in the fault tree. We'll start at the top and kind of work our way down here. So I hope that you'll walk away with at least a few ideas of how to attack some of your poorly performing control loops. I'll make the presentation available to the ISA section afterwards. So they said that James said that they posted on the website somewhere. But also I have a sheet at the back where if you would like a copy of the presentation, just leave your email address and I'll email you a copy of the presentation. If you have any questions while I'm talking, that's fine. Just go ahead and ask the question. If there's something that I didn't explain properly, there's probably a few other people in the room that had the same question, but just didn't want to ask it. So we'll start off by looking at symptoms of poor control. Well, basically poor control is when you have deviations from set point, unacceptable deviations from set point. If the control loop stayed on set point, I mean, who cares if it's not tuned properly, who cares if the valve is working properly, but what we're talking about is loops that deviate from set point and it's unacceptable and you'd like them to stay on the set point much better. Many of these loops are so problematic that the operators go and put the loop in manual control. They find that, it's in auto, the loop is actually worse in auto than what it is in manual. So you'll find a couple of loops in manual that are performing so poorly. And then other loops, they may oscillate, they may go completely unstable. The valve might be like hitting into the bottom limit or the top limit of the control range. The loop might just be really sluggish. Right? There's a disturbance hits the process, and man, this loop just doesn't get back to set point as fast as you'd like. There may be really large deviations from set point. Also, you'd like to stick closely to set point because it's critical for the process, but your process just doesn't stay to the set point. You can also have excessive controller output movement. Right? The valve is forever opening, closing, opening, closing. It may be that we're keeping the process to set point, but we're creating havoc in this downstream process with the valve opening and closing the whole time. So various symptoms of poor control, and we'll take an in-depth look at each one of these symptoms and what could be the causes. And what I'll use there is this problem analysis tree. So we'll start at the top, controller manual, and so on, and work our way down. The control loops in manual. Right, some loops are fine. They're part of the process that we designed. It's a redundant piece of redundant pump. It's got its own little flow loop on this pump, and loops in manual, and that's fine. We're not talking about those loops. We're talking about loops that are in manual that are really supposed to be running in auto. Okay, so take an audit, you get a list of loops that are in manual, and you weed out the ones that are supposed to be in manual, and you end up with the ones that are in auto. Now, the operator would normally be able to tell you why this loop is in manual. And his explanation might just be, well, it doesn't work in auto, which doesn't help you much. Or he may be able to tell you exactly why it doesn't work in auto, in which case it helps you. Typically, you have to go back and review historical history of fine pieces where this loop actually was running in automatic control, so you can see what the problem exactly was. Or alternatively, you can ask the operator to put the loop in manual so you can see exactly what the problem is. You can always put it back in auto. Put the loop in auto to see what the problem is. You can always put the loop back in manual. But once you see what the problem is, then we can go down the rest of this fault analysis tree and find out exactly how to solve this problem. So we assume we put this loop in auto, or it's been running in auto all along, and we have to differentiate between if the problem we have, these deviations from set point we have, whether they are oscillations, because there's a whole different fault tree for them, or if they're random deviations from set points, in which case we'll take a different path down the street. The differentiation there is pretty easy, but it's a very important differentiation because it'll take you on a different path. Now, some loops have a little bit of oscillation, they have a little bit of randomness to them, and you might have to follow both of these patterns eventually to get the loop performing properly. But here you go. Oscillations, periodic. You can use some software to analyze, do a power spectrum analysis and so on, but you can normally just look at a loop and see, well, is this a persistent oscillation, or is it like more random? We'll take the example first of an oscillation. So we'll say, well, this loop is oscillating, and I spend a lot of time looking at control loops at plants, and you guys should probably know also that oscillations is really one of the big problems that you have. There are many, many control loops out there that do oscillate. I would say probably between these two, I don't know exactly what the ratio would be, but my guess would be that maybe problem loops, it's maybe a 4-to-1 ratio that, well, this loop is oscillating because of some reason. So oscillations, it's a severe problem in control performance. Now, oscillations can have various causes. It could be externally caused, meaning it's not really coming from within the loop. It could be internal, the loop itself is causing itself to oscillate, or kind of a combination between the two, a cyclical interaction. So we have to differentiate, first of all, we need to know if it's an externally caused problem or an internally caused problem. If it's external, we're going to go find it somewhere else. If it's internal, well, we're at the loop, it's oscillating, we're right there, we can work with the loop. How do we differentiate then between if this is an external problem or the loop itself causing the problem. Well, surprisingly high-tech answer. Put the control loop in manual, put the controller in manual and see if the oscillation stops. If the oscillation continues, then it's not this loop causing the oscillation. That's pretty clear. Right, so we put the loop in manual, oscillation dies out. Well, it's probably this loop. There's one alternative to it that I'll get to later. But if the oscillation persists, well, then it's somewhere else, and we've got to go find where the oscillation is coming from, and then go fix it at that particular control loop. So if it's externally caused, it could be coming into the loop through the set point, or it could be coming into the loop from the process side. If this is put the loop in manual, the oscillation persisted. So we got two options there, through the set point or through the process. Now, through the set point it might seem easy. Okay, so we take a look at this loop. It's oscillating as it's set point oscillating. Yeah, set point's oscillating, so it's obviously coming from the loop driving the set point. But not always. There's one exception to that. If we look at this cascade control arrangement, the flow loop is oscillating, let's say, and the temperature is oscillating. The set point in the flow loop is actually oscillating. So we're thinking, well, the flow loop, it's not it causing it because the oscillation is coming into the set point. But that's not always the case. If we have a sticky control valve here, and this loop is trying to get to set point, in the meantime, this temperature is not on set point. So we get some reaction from the temperature controller. And then when this valve slips to the new position, the temperature gets affected, and it may look like that, like it's actually the temperature loop causing that oscillation because it's coming in through the set point, but in fact it's not. In fact it's inside of this loop. So we have to find out if the oscillation comes to the set point, if it's actually coming in through the set point, or is it just as a result of this poor performance in this loop. And again here, the test is quite easy. We take the temperature controller and put it in manual, or the external, in my example, the temperature controller could be anything else. But we take the primary loop in the cascade arrangement, put the controller in manual, and then see if the secondary loop still oscillates. If this was a sticky control valve, like in my example, this loop would continue to oscillate, so we can give the temperature controller, put it on the side for now, and just focus on the inner loop. Right, so oscillation is coming into the set point, it's not necessarily coming into the set point, so just know about that. Right, assuming that it's not coming into the set point, it may come into the process. So we've got this loop, it's oscillating, we put it in manual, it's still oscillating. The whole process is oscillating. There may be 4 or 5 loops oscillating at the same time. These are difficult to track down. We may have this loop here somewhere that's oscillating, causing half of this process to oscillate, and we have this critical loop down here that we really want to stabilize, but it's the whole process is oscillating. How do we know where this loop is actually coming from, where this oscillation is actually coming from? There are software tools available that helps you in running these analysis. I have some experience with them. It surely does not replace an engineer. You've still got to understand your process. You've still got to do your own analysis and so on. It's just a tool. It makes it a little bit easier for you. So there's software available to help you, but quite often you've got to look at your process flow diagram, use a process historian, take a look at, well, which loops are actually around this process, which loops are oscillating, which loops are stable, and then how do they feed into each other process-wise? How do they feed into each other? So a few things you can do there is you can look for the leading oscillation. So we have a bunch of loops that are all oscillating. We don't know which one is actually starting it. We can look at the leading, the one that happens first, the one that peaks first before the others peak. We might have 5 loops oscillating. This one peaks first, and this one peaks, and this one peaks, and that one peaks. And so it's likely to be the first one. A little difficult though is the cyclical oscillation, because then you're just chasing your tail. An additional piece of information is you can take a look at the distortion on the trends that you're looking at. Distortion means how closely does it look to a recognizable signal? Does it look like a sine wave or a square wave or a triangular wave? Or is it like just really messed up and noisy? The closer the loops are to the source of the oscillation, the less distortion there will be on the signal. So just for an example here, we have a bunch of loops here oscillating, and this triangular wave to me seems like it has the less distortion on it. So that's likely the loop that I'll be looking at first. Okay, so you can look at the leading oscillation, leading peaks, and look at all distortions. Use a process historian or use process interaction analysis software to help you with this. Right, that's to pin down the problem. Eventually we'll end up with the control loop that's actually oscillating. Right, so now we've tracked it down. This loop, this is the problem, and we now have two options. It's in the loop itself. Sometimes it may be the transmitter, but most of the time it's not. Most of the time it is either the tuning on the controller or it's the final control element, valve, damper, may even be a variable speed drive. First problem, very common problem, is sticky control valve. This valve doesn't slide very well. It sticks whenever the controller just hesitates for a moment, the valve sticks in place. Then what happens, so it may stick, so this, we're looking at the set point is the green line here, and the process variable is the blue line. I think it's a flow loop, this one. So the process is above set point, and the controller then works its way down, trying to close the valve, trying to get the process to set point, but this valve is sticking in place, so the valve is not actually moving. It's just the controller output that's moving. And it's building up additional pressure on the diaphragm of the valve, but the valve's not moving. Eventually the pressure gets so much that the valve slips to a new position, but now we have excess pressure in there, so the valve overshoots its set point, the process overshoots its set point, and the whole thing just reverses direction now. Now the controller sees, well, now we're below set point, has to work the other way, so we find this stiction. You can look at the shape of the controller output. The controller output normally looks either triangular or more like a sawtooth, as in this case. The process variable is either a square wave or also maybe something like a sawtooth. You can also do a stiction test in manual. Put the control loop in manual and then make small changes in the controller outputs. Change it down by preferably 0.5% at a time, depending how tightly you want the controller to be. Make small changes in the controller output and make sure that the process variable, that the flow rate actually moves every time you move the controller output. In this case, this example here, we move the controller output. Well, this is quite an extreme example, but you move the controller output down, the process did nothing. Move the controller output again, the process did nothing. Move the controller output again, now the process responded. So it could be deadband, but if we carry on with this, we'll see the stiction. If we move the process again, if we move the controller again, process doesn't respond, move the controller again, process responds. So we're just with these successive controller output movements, we're building up pressure, the valve doesn't actually move, and then the valve moves. Building up pressure, the valve doesn't move, the valve moves. If this is the case, you really can't fix this with tuning. We really have to address that problem at the valve. It may be that the valve, that the packing has been overly tightened, and so it's sticking. You might not want to untighten the packing. Maybe the packing needs to be replaced. Maybe the positioner is faulty. Maybe the actuator is undersized. Right, so various problems there that can be causing it, but it's not a tuning problem. The bad thing would be to see this oscillation. Hey, okay, so this loop is oscillating, I'll fix it with the tuning. So you go to detune the controller a little bit. The oscillation looks maybe a little better. Detune the controller further, and eventually you detune the controller so much the oscillations now stop and you're happy. But now you have two problems. One, you still have the sticky control valve, and you have the severely detuned controller. So we're going to test for stiction, identify stiction, fix it at the control valve, not with tuning. When I started in this game, positioners weren't very common. Nowadays, almost all valves have positioners on it. Positioners also have their problems. This here, this is a step test that we did in manual, the controller output, change the controller output. This is just a simple flow loop. You see there's overshoot and then coming back. And again, we made a change. The flow overshot and came back. The positioner is doing too much, it's pushing the valve too far, and then realizing, oh, I made a mistake, and it pulls back on the valve. Now you have a positioner working like that, and you have a controller that's tuned quite aggressively. The two begin hunting against each other, and this loop starts oscillating. So check for position problems too. Positioners, they have tuning settings. They need to be calibrated properly. A positioner, some of them have auto-tunes, I guess many of them, but nowadays the digital ones all have auto-tune. But it doesn't always give you the right. Run auto-tune twice and see if you get different numbers. You'll be surprised. Again, it's a positioner problem, so we've got to fix the problem at the positioner and not with the tuning of the controller. Valve sizing. Just earlier this week, I was helping a company that had a pressure control problem. And the valve was operating, the control valve, was supposed to control the pressure, was operating between about 5% and I think 12% open. That was about the range of the valve. All right, so that valve is about 8 times oversized. It's just running at a fraction of its range, which is theoretically not a problem, but practically it's a problem because you can't, the valve position, you can't change the valve position in infinitely small increments. So you're lucky if you get like 1% or 0.5% or so out of the valve. So let's say we got 0.5% resolution out of the valve, but the valve is 8 times oversized, so that effectively is a 4% resolution that we have on the process that we're trying to control. And in this company, it wasn't good enough. The loop was oscillating. So be sure that your valves are, I mean, you can spend a lot of time trying to tune valves and replace them and try and get rid of stiction and so on, but if the valve is oversized, that's not the right, or it's not the only solution you need to look at. You also need to look at replacing the trim in the valve to get it sized properly, or replacing the valve. Another problem, non-linearity. Got an equal percentage valve. It's a flow loop. It's a flow application, so we put an equal percentage valve in there. But do you really need an equal percentage valve? Not all loops need equal percentage valves, even if it's a flow loop. So we end up with this flow characteristic, which is not linear, and we end up with a controller that's kind of sluggish at low flow conditions, and a controller that's really almost out of tune under high flow conditions. So you've got to use a characterizer then, or change the trim in the valve, or change the valve to get a linear characteristic, linear installed characteristic. Characterizer is pretty easy to implement. You can also have nonlinear processes like pH. When you control pH, it's a very nonlinear process. A single controller gain is not going to work all the way through your pH range, so you have to do some gain scheduling to adjust your controller gain depending on what the pH is.
Can you expand on that a little?